Alright, this is a broad overview of some of the information that you are responsible from the summer assignment. First off is the organization of matter. Matter is anything that takes up space and has mass, can be divided into mixtures and pure substances, which can then be divided even further. There are some important properties of matter that need to be discussed. The first is extensive properties. These are properties that depend on the amount of matter that's present. And there are also intensive properties, and these are properties that doesn't matter how much is present. So some examples of an extensive property is volume, mass, and also the energy content, like calories. And then there's also intensive properties. So these are the ones that don't depend how much is there, like melting point, boiling point, density, and so on. So these are some important distinctions in the properties of matter that are important to keep in mind. Next up is sig figs. All of you should have received a handout on sig figs. Some of the things that people tend to get tripped up on is non-zero digits are always significant. A zero is significant only if it's the last number and also right of the decimal. It has to be both. So if you have 4.30, then that zero is significant. Zero is also considered significant if it's sandwiched between numbers like 403. When we're talking about multiplication and division, the term that has the least number of significant figures, which would make it the least accurate, is the one that determines the answer. So in the example given here, 4.56 multiplied by 1.4, your final answer is going to have two significant digits because the least accurate measurement, that 1.4, only had two significant digits. For addition and subtraction, you're also looking at whatever is the least accurate measurement. So the term with the least number of decimal places is going to determine the amount of significant figures in the final answer. So in the example given here, you have three numbers that you're adding together, and one of them only has three significant digits, so your final answer is also going to have three significant digits. Dalton's atomic theory is pretty important. It's all built off of an initial work done by someone named Lavoisier, and he came up with the law of conservation of mass, which is essentially mass is neither created or destroyed. And that happened in the late 1700s, and from there a bunch of work was done, and one of them is Dalton's atomic theory, which is important, and that was in the early 1800s. So in Dalton's atomic theory says that each element is made up of tiny particles, and those particles are called atoms. The atoms within a given element are identical with their size, mass, and other properties. And then if you compared those atoms to atoms of different elements, you would see that they are different in size, mass, and other properties. He supported the idea that atoms cannot be created, subdivided, or destroyed, and also said that when you form chemical compounds between elements, the name of combining different types of elements together were chemical compounds. And lastly, in chemical reactions, atoms can be combined or separated or rearranged. That's what makes something a chemical reaction. There are some things that have been more recently disproven as it comes to Dalton's atomic theory. One of them is that when he said that atoms of a given element are identical and etc., etc., modern theory says that atoms have a characteristic average that is unique to that element. Dalton also said that atoms cannot be subdivided, created, or destroyed, and what we know now is they can't be by ordinary chemical reactions. However, in nuclear reactions, these things can happen. The next step when it's talking about early chemistry that's important to keep in mind is the discovery of the electron by J.J. Thomson. He used something that he called a cathode ray, and basically it was a large tube that had two electrodes on either side, and when he put that entire tube under high amounts of voltage, he noticed that a ray was produced from the negative end, and Thomson postulated that that ray was composed of negatively charged particles because not only did they start from the negative end, but they were quickly repelled from that negative end towards the positive electrode. So the cathode ray tube passes electricity, and there is a gas inside at low pressure. Okay, so Thomson postulated that this ray was composed of negatively charged particles that was considered to be the electron. He went on to say that we knew that there was some type of atom, and we knew that the atom was made up of particles, but we weren't quite sure, not we, because I obviously was not around, I don't know why I'm saying we, but they weren't quite sure what it looked like. And Thomson came up with the plum pudding model, which is basically that the electrons were sprinkled all around positively charged pudding. Another important discovery to mention was in the early 1900s, someone named Robert Millikan determined how big the electron actually was. He had something called an oil drop apparatus, and basically he took charged oil and he would drop it through this container, and at different parts in the container he had large amounts of voltage, and he could actually stop the oil from dropping through depending upon the voltage. And he's going to do some fancy math, well, he did some fancy math and came up with the mass of the electron by looking at the mass of the charged oil particle. So that was Robert Millikan. So the important things to remember when it comes to the electron is that the cathode rays, they have identical properties regardless of the element used to produce them. So basically he could create the ray in his cathode tube in a bunch of different ways, but the properties of that ray were always the same. So he concluded from that the elements, that the electrons in elements all must be the same. Atoms themselves are neutrally charged, so there's got to be something that balances out that negative charge. So from that, they were able to deduce that there must be positive particles in there as well. Finally, electrons have so little mass, and that's from Millikan's experiment, that something else has got to take up the bulk of the weight, or the mass. Okay. So all kinds of things just happened. My phone rang, people were walking in my room. So I started over from this point, so if it was an awkward transition, it's because I clearly have no idea what I'm doing. But anyway, let's move on to Rutherford's gold experiment. According to the plum pudding model, Rutherford expected that when he took massively big alpha particles and passed them through a gold foil, he expected that they would pass directly through with very little deflections, right? If they're just tiny electrons that are sprinkled randomly in a positively charged pudding, that these big, large alpha particles should be able to travel through that with no problem. But in fact, when he did the experiment, what he found was that they were actually deflected at very large angles. And in fact, some were even reflected back. And so from those results, he reasoned that the plum pudding model could not be correct because the large deflections could only be produced by a center of concentrated positive charge. So just a little bit more information on that. The alpha particles that he used in this experiment were helium nuclei, and they were fired at a very thin sheet of gold, and he was able to detect what happened to the particles because he had some film around the outside, so he could see where the particles landed. All right, moving on to ionic charges. When we're predicting ionic charges, we can use the groups to help cue us what the charge should be, because everything in group 1 is going to lose 1 electron to form +1 ions. Someone with group 2, they're going to lose 2 electrons to form +2 ions. We move all the way across the transitions to group 13. Now we've got elements here that are going to be losing 3 electrons to form 3+ ions, like barium. We can continue on, but things, okay, that said group 14, and it went away. But group 14, they lose or gain 4 electrons. One note when we're talking about ionic charges here, C2, 2 minus, and C4 minus are both called carbide, and people can get tripped up by that. Moving on to group 15, these elements are going to gain 3 electrons. And one thing to note on the names there, even if we go here, nitride, phosphide, okay, there's patterns to the names. Group 16, they're going to gain 2 electrons. Group 17 is going to gain 1 electron, fluoride, chloride, bromide. And then finally, group 18, these are the stable noble gases, and they're not going to form ions. If we do go farther into the transition metals, many transition metals actually have more than one possible oxidation state. So you can look at iron. Iron can be +2 or +3. But some of them don't. So zinc is always +2 and silver is always +1. When we're writing ionic compound formulas, for example, if we're going to start with barium nitrate, the first thing that we're going to do is write the formula for the cation and the anion, including their charges. So we would look at the periodic table and we would see that barium is going to be +2. Nitrate is one that you should have memorized, is going to be -1. And we look to see if they're balanced. And we would see that they are not. So to balance the charges, you're going to use subscripts. If you have a polyatomic ion like nitrate, you're going to use parentheses. So there's our beautiful parentheses. Now we've got to balance the charges. And I clicked a little faster than I want to. So we're going to balance the charges. And you get to see it all again to this. Okay, let's try another. Ammonium sulfate. Don't hesitate to pause it and try and write this one yourself. So we're going to write the formulas for the cation and the anion. There's our ammonium. There's our sulfate. We're going to check to see if the charges are balanced. I probably wouldn't give the example if they were. So we're going to use parentheses and balance. Okay. Next, iron 3 chloride. Remember, if the iron has the 3 on it, it means it's the 3+ chloride. Again, check to see if the charges are balanced. They are not, so we're going to use parentheses if we need to, but it's not a polyatomic ion, so we don't have to. Now, again, these are ionic compound formulas, so in an ionic compound formula, you would include the charges on the ions. So chemical changes involve reorganization of atoms. You have reactants going to products. When the equation is balanced, it has significance. So here in this one, we have 1 mole of ethanol reacting with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. That is a quantitative significance, meaning it tells us how much is produced. Now, there are problems that need to be calculated when it comes to these. And for this section of the PowerPoint, I'm going to record a second one. So we'll stop this one here.